Welcome, everyone, to this new meeting on the Financial Line seminars. And it's a real pleasure and a privilege to introduce today's speaker, and Professor David Danks. David is Professor of Data Science and Philosophy in the affiliate faculty in Computer Science and Engineering at the University of California, San Diego. His work spans a wide range of topics at the intersection of philosophy, cognitive science, and artificial intelligence. And David has made substantial contributions to the ethical, psychological, and policy dimensions of AI and robotics, with applications in areas such as transportation, healthcare, privacy, and security. He's also well known for his research in computational cognitive science, particularly in the development of innovative causal discovery algorithms for complex observational experimental data. His achievements have been recognized through several prestigious honors, including a James McDowell Foundation Scholar Award and Andrew Carnegie Fellowship. He holds an AB in philosophy from Princeton University and a PhD in philosophy from UC San Diego. And before returning to University of California, San Diego, he held the position of Thurston Professor of Philosophy and Psychology at the Carnegie Mellon University. And today, he will be presenting on a highly timely and important topic. And the title of his talk is Challenges of Explainable AI. And I'm very much looking forward to hearing his insights on this complex and evolving issue. And as always, after the talk, we will open the floor for discussion. Please don't hesitate to raise your virtual hand via Zoom if you have any questions or comments. And thank you once again, David, for accepting our invitation, and the floor is yours.
Thank you so much, Emiliano. It's really a pleasure to get to talk to all of you today. I suppose I should say good morning to those of you who might be on the west coast of the US with me. Good evening to those of you who are in Europe. Thank you for staying connected even later in the day. I should mention as I'm going through this talk, I would be perfectly happy to be interrupted if there are questions that come up, whether people want to raise their hands or drop them into the Zoom chat. I guess it's a sign of the world we live in now that we've all gotten used to the idea of giving talks while also monitoring a chat box that is elsewhere on the screen. So happy to do that. So what I wanted to do today in this talk is to talk a little bit about some issues around explainable AI. Some of this is going to be, I think, a bit more philosophical in nature. Some of it is going to be empirical and psychological. I think that we're now in a place that pretty much every document, every call that I see around ethical AI, responsible AI, makes reference to the importance of explainability and the importance of transparency and the importance of us understanding how the AI works and these kinds of claims. And so what I want to do today is, I guess, the big picture goal is in some ways to actually tamp down some of the enthusiasm. I think that explainable AI systems are incredibly nice to have. I think there are many cases where we enjoy having them, and we might even want to try to build a system that is explainable in some ways. But I think it's not this ideal goal that it is often presented as. I think sometimes people seem to talk or write as if we just had explainable AI, then everything would be okay. We'd have trustworthy and responsible AI, and it would be ethical, and everything would be magically perfect. I think that's wrong. I think explainability is one tool that we have in a very large toolbox of ways that we can try to make sense of an AI system and the implications that it has on us humans. And so that's sort of the big picture background for today's talk, is a sort of skepticism that explainability is actually as wonderful as a lot of people think it is. So why do we think explanations are valuable? Here I'm going to be adopting the standard framing in philosophy of explanations as answers to why questions. So if I want to know, why is the shadow a certain length? Well, because the flagpole has a certain height, right? To use the classic example from Hempel in the 1940s. More generally, if I want to know, why was this person denied a loan? Well, if it was, a loan decision that arose because of an explainable AI system, then we really ought to be thinking to ourselves, okay, well, why did the AI system give the answer that it did? Whatever uh, response I give to that why question is going to be an explanation. So when we think about explanations, I think there's multiple reasons why we might want them. One obvious reason is for prediction and inference. If I want to be able to predict what my system is going to do or how a person is going to behave, in this case of explaining a human, not an AI, when contexts change, I need to know something about why they behave as they do. So, if I want to, if somebody wants to know how will I respond this weekend when I go to the graduation ceremony here at UC San Diego, because our academic year is finishing, um, if somebody wants to predict my behavior in that new context, I've never been to the UCSD graduations. I've only been here 4 years and haven't gone yet. But somebody who knows me might be able to make a pretty good prediction because they can explain what drives my behavior. Or if we want to know what happens when the system changed. If I want to know, what would happen if my car were suddenly struck by lightning, I need to know something about why my car behaves as it does, why it performs as it does. If I have an explanation for my car's behavior, then I probably am going to have some information about how it would behave if it were struck by lightning. In a way that if I, treat it as a black box, my car, I push the accelerator, it goes. I push the brake, it stops. If that's the only understanding I have, then I'm not going to have any clue how it's going to behave if it's struck by lightning or if it's suddenly sitting in 1 meter of water or something like that. Um, we also want explanations because we want to control our world. We don't just want to passively sit back and watch the world happen. Often we want to control or manipulate things. And so we want to know why a system behaves as it does, because that can tell us how we can reach in and wiggle things, how we can reach in and perhaps break things to stop some unwanted behavior, or what changes or adjustments would enable us to have more success. And then I think another value of explanation that needs to be recognized is just the sort of epistemic joy that we receive. We humans like getting explanations. Explanations are fun, they're good, they bring a certain kind of subjective pleasure to people. The psychologist Alison Gopnik sort of once famously or infamously wrote a paper with the title Explanation as Orgasm, right? The idea being that there's an intrinsic value to getting explanations that goes beyond the pragmatic values of the previous two bullet points. Right? So we want to make sure to acknowledge that, part of the reason we want explainable AI is it's just cool to understand how these really complicated systems work. Now that's, I've been thinking about talking sort of generally about explanations. When we think about AI, um, we have specific terminology for some of these things. So when we want to be able to predict how a system is going to behave in novel circumstances, in new contexts, we think of that as generalization. And so the idea would be that explanations or explainable AI systems, it's not that they will necessarily generalize better, but rather it's that we will be able to predict accurately when they will generalize to a new context. So if I build an AI system to do disease diagnosis here in San Diego, and I want to predict whether it's going to work in Rome, then having an explanation of why it works here in San Diego will help me to know why it works in Rome. If one of the things is that if one of the reasons that it works is that the medical files are written in English, then I've got a pretty good reason to think it's not going to generalize to Rome. But if what matters is that it's at an academic medical center, then it will generalize to some hospitals, presumably in Rome. But it won't generalize to, for example, a rural clinic out in the countryside here in California. Similarly, sorry, I should say. And so, of course, why do we care about generalization performance? Well, that helps us to think about where we might want to deploy the system. Where are we going to be willing to use it? If I don't know that a system is going to be successful in a new context, I probably shouldn't be deploying it to that context. If we want to be able to predict what happens when the system changes, well, that's useful for things like troubleshooting. So if my AI misbehaves, if it gives an answer that seems very surprising, well, if I can explain how it works, then it's going to be a lot easier to figure out what went wrong in this particular case. If something changes, if the if the underlying random seed gets corrupted in some way, such that it's always using the same random seed, so I'm getting behavior that's surprising, then I can troubleshoot that if I understand how my system works. If it's just, it does things, then I'm not going to be able to. And this is particularly important when we think about issues of governance or recourse. So we want explainable AI in part because we think it will help when I am denied a loan. If I think that that was unjust in some way, then I need to understand how the loan approval algorithm worked in order to be able to actually do something different, to have some recourse, to be able to change my profile so that I get a loan approval decision rather than a loan rejection decision. When we're thinking about control and manipulation, we want to improve our systems. If we don't know, if I've got a black box AI and I don't know how it works, then improvement is sort of a guess and test strategy, right? I tweak something, I wiggle something, but I have no clue if it's going to help. But if I understand how the system works, then I can tune particular aspects of it to try to improve performance. It's one of the challenges that we have right now with these very large deep networks is exactly that we don't understand necessarily how they work. So if I want to improve performance, you have to use very sort of uh, blunt mechanisms or methods like reinforcement learning by human feedback, or LHF, where I'm just sort of nudging the system in what I think is a better direction, but I'm not able to do it in a targeted way. Whereas if we understand how a system works, we can improve it in a much more targeted way. So, one very obvious example of this is when people worry about things like biases or different kinds of structural injustices that might be built into our models or algorithms. Well, we want to get rid of that. But how do we get rid of that if the only thing we can do is basically retrain the whole model or do a very simplistic adjustment by some sort of reinforcement learning slapped on top? So, if we want to be able to be more intelligent about how we improve our systems, it seems as though we need to know something about how they work. And of course, epistemic joy is epistemic joy, right? Just as little kids enjoy understanding how a toy works, big kids like understanding how an AI system works, that there's real joy there. So, those are sort of the functional reasons why it might be so useful to have explanations. When we think about explanations themselves, obviously there's a few hundred, let's say few thousand year history of this in philosophy, trying to understand the nature of explanations. As I said, I understand them as answers to why questions, a very standard way of thinking about it. And of course, we can ask multiple why questions about the same phenomenon. So if I ask, my AI system says, deny a loan to Emiliano. Don't give him the loan. Sorry, Emiliano. Then, I can ask, well, why did it deny the loan to Emiliano? Why did it deny the loan rather than an approval, right? So turn it into a contrastive question. I can ask why, why do the training data matter in making this decision, right? So I can ask a sort of more historical question or etiological question about the origins of the model itself. I can ask why do certain factors matter and others don't, right? Why does it care about his income, but it doesn't care about his skin color, at least hopefully, and so on. And so what that means is that actually for a single phenomenon, we can almost always have multiple explanations. I think that this is not a terribly surprising thing. You can at least, go at least back to Aristotle, for causes, if not, further back in terms of trying to, find people who recognize that for a single phenomenon, one thing that, or an event, you can have different kinds of explanations depending on what it is that you're asking about. So I think one of the first lessons that we need to have about explainable AI, and this is one that it's starting to make its way into the more technical communities, but it still is one that seems to surprise a number of technical people, is that when we think about explainable AI, those explanations are always going to be relative to a particular set of users, a particular set of goals, a particular set of needs and knowledge. Um, so the same, you could give an explanation of an AI system that works for me when I'm a bank manager trying to improve the performance of my loan approval algorithm. And that same explanation might be useless to Emiliano, who wants to know what recourse he has when he thinks he's been unjustly denied a loan. So we need to sort of make sure that we're being appropriately broad in our understanding of explainable AI, that it's not simply a matter of, for each event or phenomenon, there exists one unique best explanation. There are going to be a number of them. And I think that's reflected in the kinds of techniques that are being developed right now for explainable AI. So when we think about explainable AI, anyone who's worked in this will be familiar with the fact that there are many different terms being used. We do not have a shared, agreed upon terminology of what counts as explainable AI versus interpretable versus transparent versus any number of other things. Um, One distinction that's important is sort of where does what we might think of as the cognitive labor, where does that reside? So it could be that I've got an AI system that gives me an explanation. So I say, to my system, why did you give me that output? And it gives me an explanation. Many large language models claim to give explanations, though it's not clear that what they're giving actually are explanations as opposed to confabulations that sound good. Um, it could be that it's explainable in the sense that I, as a human, can make sense of it. Right? So it's explainable in the same way that a machine where I can see all of the gears might be explainable. So in the second case, the explainable case, what we've done is we've shifted some of the cognitive labor from the AI. It's not generating the explanation. To me, as the human, I now have to generate the explanation, but the system is designed in such a way that it's pretty easy for me to generate it. And then there's a sort of third kind of category, which we see especially in robotics, but also in some voice assistants, which I think of as interpretable AI, which is where I, as a human, can generate an interpretation that makes sense, but I have no clue whether it's actually the correct explanation. So you can think of this as the non-AI version of this is when you see your pet, your dog or your cat, say, behaving in a particular way, and you think, oh, they believe something. Well, they don't have beliefs in exactly the same ways that we humans do. It's probably non-propositional, but yet I can interpret them in that way. Similarly, if a voice assistant, I won't name any of them because I don't want to use trigger words that might activate a system in somebody's house. But if you use a assistant from, Google or Amazon, those kinds of systems, again, they act as if they have beliefs and desires, but they don't have things like beliefs and desires in the ways that we humans do. So that's a case where now the cognitive labor is shifted even more onto me as a human to generate an interpretation. So all of these things, from the system gives me the explanation to I have to do all of the work of coming up with an interpretation, all of them get the label of explainable AI right now. There are people out there who would call any of these things explainable AI. I'm a lot more interested in this middle category because I think that's where most of the technical work is happening. And there it divides into sort of two different ways. On the one hand, we have people who focus on models that it's easy to generate an explanation because it's a simple model. So they'll say things like, look, what we should really do is try to use a linear model. Why? Because I can understand a linear model. Human brains can handle linear models. And so or a decision tree, or these kinds of things. That's what explainability is about. Because if it's simple enough, then we humans can make sense of it. We can generate the explanations. The other way in which we might try and help the humans out is through post hoc methods. So these are the things like LIME or SHAP or other kinds of, if you've heard of those kinds of techniques, where you take a black box and you basically find the patterns in the black box that make it simple enough for a human. So a technique like LIME, um, local model independent or model agnostic explanations. The idea with LIME is we've got this horribly complicated model that we don't understand at all. But if I want to know why it made a particular decision, all I really need to know is where is this point, Emiliano's application, relative to a decision boundary? And decision boundaries could be locally linear. Right? So the idea of Lime is you say, all right, here's the decision point. What's the kind of linear decision boundary that's close to this point? And now I can see, oh, if I just had, if Emiliano's application had been slightly different, then he would have been on the other side of that boundary. Right? So that's the idea of Lime. We don't try and simplify the model, but we simplify the description that is provided of the model in a way that makes it human interpretable, that we can, or human we can generate the explanations. Now, all of these methods are focused on asking the question, why did the AI behave in the way that it did? Which means they are all fundamentally asking for a certain kind of internal causal explanation. They want to know, why did this system do what it did? Where the explanation is something like, well, here were the inputs. These inputs are transformed in this way. And then we've got a decision procedure that uses the output in this way. And next thing you know, we've got a decision being made. Or the AI is, why did the robot grip the cup that way? Well, I'm going to tell you an internal causal story of the transformations that are occurring of the, from the perceptual inputs to the motor outputs. So the first sort of takeaway message, the sort of first third of the talk, I promise it'll go faster as I go along, is that explainable AI is fundamentally, right now, what we do for explainable AI is fundamentally an internal explanation. It says, look inside the AI, what is it doing that produces this output? But the problem is, oftentimes we don't want that. Oftentimes, what we want to know is not why did the AI behave as it did, but rather why is the AI justified in the behavior that it performed? That is asking for a kind of external explanation. So it's not simply asking what's the internal causal story to the AI, but rather asking why is this the right output? So an explainable AI system right now can tell us why it rejected Emiliano's loan application. What it can't do is tell us why it was right to reject Emiliano's loan application. That's a different kind of explanation that current explainable AI methods simply don't give us. So one of the challenges of explainable AI is that I think what it's giving us is often not what we ultimately care about. In many contexts, what we care about is not what's the internal causal story of the AI. What we care about is, why should I believe that the AI is right? Why do I think that it's telling me accurate information about the world? Because if it's not giving me the right answer, I don't care what happened internally to it. That doesn't matter to me. If it's not accurate, if it's not reliable in the sense of giving me accurate information about the world or accurate judgments or these kinds of things, I might care about the internal structure because I want to fix it. But that presupposes that I already know why it gave the wrong answer, or that it's even the wrong answer to begin with. This is just a different way of saying this, is that current explainable AI is very descriptive. It describes what happened, but often we're interested in normative explanations, or explanations that have a normative content about the rightness of the output, not merely the causal story about why the output resulted. So what this first observation leads to, right, is that we've got this collection of methods, a very large collection at this point. We've got a large toolbox we can draw from, but it's not clear if they actually help. They help computer scientists coming up with these explanations. They look and go, yeah, this seems sensible. But the first question that we wanted to ask is, do they actually help ordinary people? So, one way in which they might help is that they would be connected to notions of trust, that an explainable AI system would be a more trustworthy one. Because if we understand why the system works as it does, then we're going to have an understanding of what the underlying values are that are advanced or implemented in the AI, which is to say, we know what matters to the AI. And so that, could come from an explanation. Why does the AI do this? Well, because income really matters for the decision. It has a high SHAP value, right? So think of that in sort of counterfactual or hypothetical terms. If I wiggled the income as I wiggle the income, I get big changes in the output decision. Okay, so I now know that I can trust this algorithm to care about somebody's income when it's making a loan approval decision. Um, so If that's right, though, then that means that the SHAP value in this case has to actually have helped my understanding. So I want to describe two experiments that we ran. One was asking the question of whether explanations improve the subjective perception of understanding. So do people think they understand things better? And then the second one was trying to really get at the question of, okay, if, I'll spoil the first experiment. Yes, people believe that giving explanations improves their understanding of an AI system. But then the second question we wanted to ask is, does this improve the objective? Do people actually understand it any better? And connected sort of to both of these, lurking behind both experiments, is the question of, do those explanations lead to improved trust? Because if we want the other kinds of goals, right? If we want epistemic joy, that's just the subjective understanding. If we want to be able to do prediction and inference, that's connected to issues of trust. If we want to be able to control, that's connected to whether we really understand how the system works. So most of the functions of explainable AI, at least in theory of the explanations, depends on these kinds of things, whether the explanations really help our understanding. And so we thought, let's just investigate this empirically. All right, so the first study was looking at loan approvals. So both of these were in the financial domain, which makes it appropriate for the finance network. And so the first thing is we said, well, let's just take two simple, let's just do a really simple experiment, right? AI systems, one's a decision tree of, I think it was a three-layer decision tree, very easy to understand. Here's a neural net model. Both of them are trained on real data, so no problems there. We actually, these are externally valid in that way. We did a pretty large at least large for some empirical studies, pre-test where people said, yep, that makes sense. Those are the features that I would expect to see, right? So these are trained on real data. People think, yes, the inputs make sense. And so then we wanted to see, all right, depending on whether you get the decision tree or the neural net, we then are going to cross the outcome, application approved or denied, with the explanation. So the explanations were you might get no explanation, control. The explanation might be, well, here are the three things that matter the most, but we're not going to tell you what's inside the black box. Or we might show you the decision tree, or we give you a neural net explanation. Now, the neural net explanation was essentially a kind of SHAP explanation but it was either the global or the local, right? So here's what matters for people like this individual, or here's what matters globally. And then the question was, basically how do people respond to these explanations? Do they think they understand them? Do they think these are fair? Do they think they can control the system better and the like? So we did a large scale study, of course, 12 conditions spread across, 1,200 people, so about 100 per condition. So, pretty good, even though the data are, as always, noisy. I think we've got pretty good reason to think that these are giving us information about people's responses. And a lot on the screen. I'm not going to try and explain all of it. What I want to do is highlight just a few things. The first is we see just a standard main effect that everybody likes things more when they get what they wanted. So if the person was approved for the loan, if the participant was, fictionally approved for the loan, they say, oh yes, I understand it better. I like the AI better, right? All these kinds of standard things that you expect to see in terms of a main effect. A second thing that we see is that as we move across the explanation modes, we see the subjective perception of understanding and satisfaction going up. Now, if you look at it, it's not a perfectly clean increase. The statistical tests, because we've got a large enough sample, the statistical tests do bear out that getting more and more explanations improve or increase the subjective perception of understanding and the subjective satisfaction. Interestingly, if you look at the way that these explanations are ordered, you will notice that the neural net is at the high end of those, which might seem a little bit weird because what we found is that the black box algorithm, people actually liked better than the decision tree, which is a little bit of an odd finding because if explanations are really what's doing the work, then you'd think that something like a decision tree where I can fully understand what's going on would be more appealing to me than a neural net. Because a neural net, I mean, it's a black box. Sure, you're giving me a bit of insight into it, but it still is this complicated black box. I don't really understand it. And yet people have a subjective perception of understanding that is higher for neural nets than it is for decision trees. Um, in fact, decision trees lower relative to the baseline of no explanation at all. They lower the perception of understanding and lower the perception of satisfaction. So we found this very odd, right? It was like, wait a second, we're giving people explanations and they like the system less. This seemed like a really important thing for us to investigate. And I think already shows something about the fragility of explainability. That when you're talking about explanations of AI systems, you have to be really careful about how you think through this. Um, and so that actually led us to do a second study to investigate this in a bit more detail, in addition to looking at the objectivity thing. So this time, what we did is we thought, well, part of what we thought might be going on is although we knew that people liked the features that were used in the decision tree, maybe they thought the decision tree was just wrong about how those features mattered. Because there were some counterintuitive things that happened when we trained the decision tree on real data. So when we train it on real data, we get these sort of, this feature is actually negative. It makes you less likely to get a loan, but people intuitively think it should be positive. So what we did is this time for study two, we said, we're not going to train on real data. We're going to ask people, what do you think? How do you think these features matter? And then we're just going to build decision trees that encode people's prior expectations about these features, run roughly the same kind of study, though this time we added in a different, another condition, which was we thought maybe it would matter if you thought, if you were the applicant versus you were the person working for the loan company. Um, and this time we didn't just get the subjective measures, we wanted to get objective measures. So could people actually come up with explanations on their own? Could they actually figure out what recourse is available? So if you're denied a loan, can you figure out what you could do to get the loan? Right? So if you've got a decision tree, I suspect for many of us on this call, if you've got a decision tree, that's not too hard. You just go, okay, I'll have to go down a different branch. How do I get down that different branch of the decision tree that results in accept? There you go. There's a recourse. Um, so what we wanted to see is whether people could have sort of appropriate behaviors given what they were learning. We also collected the subjective measures because we were curious. Now, there's a lot going on in this study. So for partially that reason, we doubled the sample size, got a lot more people. The first thing to say is that when we actually looked at the study, what we find is that the complex tree, a more complex decision tree, people correctly rated it as more complex. They seem to like it better. So the short version is that we think what happened is that people in study one, that those red arrows that were showing that, the decision tree was worse than no explanation, that seems to be a function of people rejecting the decision tree we showed them, even though it was trained on real data. Okay, so here's a second complexity about, or third or fourth at this point, complexity about explainability. If you give people explanations that conflict with their prior expectations, it's worse than giving them no explanation at all. So you have to be very careful because you might give a true explanation. You're accurately describing what's going on in the system, in the AI. But if people if that's not what they thought was going on, you can actually make things worse. Okay, so it's not as though explanation always makes everything better. This isn't like coffee where, it's always better with coffee. It's rather this sort of much more complicated interaction between the prior beliefs and expectations of the people receiving the explanation and the actual one. I mean, I think raises some interesting ethical questions of should I give explanations that are actually false, but work given the prior expectations of the person? An old problem in the philosophy of explanation, of course. And so we find again that there is now this time what we find is that the tree using a decision tree actually does improve the subjective measures instead of making them worse. And we do again, I should say, get that main effect, at least especially for satisfaction of people like the approval. They like the AI when there's an approval. Um, the more interesting part of this study, I think, is that actually there wasn't a whole lot of correlation between the objective and subjective understandings. By and large, people who thought they really liked and they thought they really understood were not any more likely than people who thought they didn't understand. They were no better at the performance measures. And so this actually surprised, in some sense, surprised some of us in this group. It didn't surprise me because I figured people were going to, there's this phenomenon called the illusion of explanatory depth that people think they understand something, but actually they don't. And perhaps unsurprisingly, perhaps surprisingly, we found that here. Um, and so what you can see, these are a little bit complicated to understand. The main thing to see is that in general, people were not particularly good. They were better at generating explanations than generating counterfactuals, but they really struggled. And especially if you look at the complex tree bar graph on the right-hand side, what those are showing, the thing to see there is the sort of shape of the bars depends on whether you were ending up, whether the individual was on the right branch or the left branch. I mean, the presentation of the complicated tree mattered, right? I mean, and so again, it shows just the fragility of these explanations. Things like, well, did I travel down the left branch or did I travel down the right branch? Impacts how much people are actually understanding. Because again, these are the objective measures, not the subjective. So this isn't whether they think they understand. This is, do they actually understand? And it depends on how I show them the decision tree relative to the individual that I'm asking about the explanation for. So there was another study I was going to show, but it's enough different. And in the interest of time, and because I want to make sure that there's opportunity for question, I'm going to actually sort of skip through this. But I just want to show this slide. I'm not going to show the details of this. I'll jump to the conclusions and not show you a bunch of the graphs. But the idea is that what we wanted to know, remember, another of the functions of explanation was potentially to help with biases. So if I can explain my loan approval algorithm, if the explanations say, oh, look, skin color matters, and in the United States, skin color is a protected attribute, or racial identification is a protected attribute, you're not allowed to make financial decisions based on somebody's racial identification. But if my model uses that, then I've got a pretty good reason to think that it's biased. How would I know that my model uses that attribute? Well, from an explanation. So what we often find right now, especially actually in the financial domain, is people are turning to counterfactual explanations to try to identify biases. So they test using standard technical methods. They test, for example, the counterfactual. If that applicant had identified as black, would they have gotten the loan? Let's suppose they didn't get the loan. If they had been black, would they have gotten the loan? If the answer is yes, well, wait a second. That means if we do this one counterfactual flip, then it changes the outcome. Standard, theory of causality here, especially a kind of interventionist theory of causality, says, well, if I wiggle something and the effect changes, then this is a cause. Therefore, racial identification is a cause of outcome. That's bad. That's a kind of bias that is illegal in the United States. So what we were interested in this experiment is whether people could actually use counterfactual explanations to find biases. So this thing that everyone's doing, they're saying, give people counterfactual explanations so they can see that there's bias or determine whether there's bias and thereby fix their model. We wanted to see if that first step is even right. If I give people counterfactuals like if the applicant had had a different racial identification, then they would have gotten the loan. If I give people those counterfactuals, can they use that to figure out, oh, this system is biased? And I'm going to skip over everything. You can see there's pretty graphs here, but I want to skip over it in terms of it. And simply say the short version of the experiment is no. People cannot use counterfactuals to identify bias. They're really bad at it. And they basically get fixated on what they think the system should have done as opposed to how the system actually behaved. So we again see a very strong effect of the prior expectations and prior beliefs. And this method that lots of people are starting to use seems very unlikely to be successful unless it's done in a very specific way. I don't want to deny there may be somebody who can come up with some very clever way of using counterfactual statements to help people diagnose bias, but the obvious way of doing it doesn't work, at least in the study that we developed. Um, so, I mean, where do we end up, and why did I call this the challenges of explainable AI? Well, part of it is I think what we find when we look at the actual empirical data is that it is far messier than those initial slides suggested, right? This story that I think often gets told, whether in philosophy papers or public policy white papers, or even some technical work on explainable AI, you often see this sort of simple story that says, um, lots of things we want to do with AI systems require us to know why they function as they do. Explanations are answers to why questions. Therefore, explanations are a good. They are a thing we should aspire to. And what we've been finding, whether you dive into it on the purely philosophical level, that was the first few slides, or if you look at the empirical responses that people have, is that it's much more complicated than that. That simplistic idea, that simplistic argument sounds good. And there is, I want to be clear, I think there is a kind of high level sense in which I go, yeah, I guess that it might work, but the details matter. And so, for example, when we looked at the subjective responses, what people thought they wanted, what people said they liked, it turned out that there were these, it depends on things like the goal or the intent, like why am I interacting with the explanation, or what kind of explanation have you given me, or what is my prior belief and expectations, which suggests that if you want explanations to be effective, you might actually have to give individual specific ones. We might need to start to develop methods or practices so that when I look at a system or Emiliano looks at a system, we're actually getting different explanations. Not because we're trying to, not because somebody's trying to deceive us or mislead us, but because we each need different explanations in order to make sense of what's happening. We need to be careful not to think, oh, people like the explanation, therefore it provides the functional benefits. As often happens, whether we think about, our students, just because they like our classes doesn't mean they learned in our classes. Over and over, we find this feature of human cognition that things that we like, even if we think we're understanding, that doesn't necessarily tell us that we really do have an understanding that can enable better performance. Um, and so, and then when we add to this for things like bias and other cases where we start to get into some things that involve morality, it's even more likely that we're going to struggle, I think, to come up with explanations that simply work in the way that we want them to. And I think that the core, and I hinted at this earlier when I talked about the complexity that explainable AI often doesn't give us what we care about, is that in many of these cases, when we did the sort of subjective debrief of participants, when we would talk to them afterwards. Now, this was obviously, as you can guess, when we have over 2,000 participants, we're not talking with all of them, but we talked with some of them. We did some follow-up with people who were willing to have a follow-up conversation. What we often found is that what people really cared about was not why did the AI give the answer it did, but why did the AI why should I, as a human, believe that the AI gave me the right answer? Right? That many of the times, the explainable AI tells people, again, the internal causal story. But what people really want is the external normative story. And we simply don't have methods for that right now. We don't have explainable AI techniques that enable us to, for example, specify why this system behaves in normatively appropriate ways, which is not about the internal causal things. I don't need to know what's going on in Emiliano's brain in order to say he acted in a normatively appropriate way. Instead, I need to know something about the relevant values, the socio-technical context, and the like. So I want to suggest a fundamentally different approach to explainable AI that emphasizes these external factors rather than the purely internal ones. So with that, I'll say thanks, and thank you to my collaborators on these different experiments, and happy to do questions for the remaining 11 minutes.
Thank you very much, David, for this rich and stimulating talk. I guess there are questions coming from the audience. So to ask question, please raise your virtual hand using the Zoom menu. I mean, otherwise I have a question just to break the ice. Okay, no, I see.
Yeah.
Okay, Maxine.
Oh, yeah. Hi, nice. Thank you for the thank you for the great talk. So my question is, so nowadays these large language models, they have this function of reasoning that they provide. Do you think these the reasoning step counts as the external, like how AI reason, why it does what it does?
Yeah, it's a great question. The quick answer is no, I don't think it does, and let me explain why. First is that I think the reasoning models. One of the things that, and we have, we're currently in the design phase of an experiment to test this. Our hypothesis that is that in the reasoning models, there's an enormous amount of human cognition that's going into the interpretation of it, but actually the systems themselves, they're reporting internal connections. So when they're giving that, what the reason we think that it looks like they are giving us a good an external explanation is because we are bringing our knowledge to bear, but the systems themselves aren't actually able to give us that directly. So it's in that sense very dependent or reliant upon our particular human cognition. Now, the other reason I think that they're not doing that is we're already starting to see, I mean, we knew this, I knew this was, I'm not surprised at this, but I guess it was just last week, there was the paper out of Apple Research basically showing that most of the reasoning models are actually not doing very much that we would call reasoning. What they're doing is stepwise memorization. And that is kind of to be expected, I think, given the way these models are trained and everything we know about their performance. So I don't think we're there yet. I want to be clear. I do think you could have models that give external explanations. So if you had a reasoning model and if every step was appropriately, involved appropriate grounding in documents, and there was maybe something else that was a sort of external justification that these are the right documents, right? Because, I mean, it could give me a reasoning model that gets to a conclusion entirely based on documents from conspiracy theorists or people who think the Earth is flat, right? That's going to be a perfectly good internal reasoning step that is externally not useful, of course. So I think there are ways of doing it, but I don't think what we have right now is going to get us there.
Yeah, and I have a quick follow-up. So I think what you said is if we have a correctly calibrated reasoning model, that could be external. But the thing that you said at first, it seems like a stronger condition that you want the AI system itself to have like a normative reason. That seems to be demanding the AI system to be conscious in the that seems to be too high a bar to.
So I don't. All right. So I don't think that I think that an external explanation or an explanation that this is the normatively correct thing. I don't think that it requires the system to itself recognize that what it's doing is normatively correct. So thank you for pushing back on that. You're absolutely right. We don't that would be too high of a bar. What I meant was simply that we have reason to think that the sequence of utterances, um, at the very least, they aren't that sequence is not for the right reasons. It's not whether the system knows that they're for the right reasons, but that you would not be able to give an external explanation that it's doing it. It's like, if I just had a random, I mean, this is an extreme version, but I have a random sentence generator and it gives me A, if A, then B, B. Well, you know, sure, that is a legitimate sequence of reasoning, but it's not happening for the right reasons. And so I think the reasons for the reasoning steps matter. It's not that the system has to have a meta awareness of the reasons for the reasoning steps. At least I sure hope not, because we humans often don't know the reasons for our reasoning steps either.
Yeah.
So,
Yeah.
yeah, I wouldn't want to hold it to a higher bar than I hold my fellow humans.
Yeah. Thank you.
Yeah. Anne-Marie.
Thank you, David. We have another question coming from Anne-Marie Butler. So thank you,
Yeah,
Anne-Marie.
thank you. That was a terrific talk. My questions are about experiments 1 and 2, although I wasn't surprised by experiment 3 because people are notoriously bad at counterfactual reasoning, right? So they don't know what to hold constant, what to change, and you get wildly different results depending upon what they do hold constant or what they change. But what I was wondering was, you've made the point in print about how what metrics you use or how you design the algorithm or even the interpretation of what the algorithm shows can be very different for very different people. And what I'm wondering is, did you control in the experiments to make sure that the people understood how the decision was made? Because what I'm wondering is if the result is that people expected different decisions, maybe they had a disagreement about how to understand this. So your comment about student evaluations is really exactly on point. My experience has been that on a Likert scale of 1 to 5, students disagree about what a 4 means. And so similarly, as you're giving them this kind of complicated decision tree or algorithm, um, there may be subtle differences in expectations about what this metric means or what the thresholds are. And so I was wondering if there was a way to kind of control for that.
Yeah, so the that's a great point. That what does a 4 mean on this 1 to 7 scale is that we would expect there to be significant individual differences in that. Different people are going to interpret it in different ways. That there are ways to control for that. The big way to control for it is that you do a whole lot of pre-training with your participants to teach them what the different things are supposed to mean. The risk there is that you're teaching them a lot of things other than just what the anchor points are on the scale. And so the risk is that what you're doing is turning them from we wanted people who were relatively untutored when it came to what counts as an explanation or what you should look for in an explanation. So that was actually part of the reason that we ended up running it with 1,200 participants. I wanted to go back to this just because it does show you the error bars on these. They we do for each of these bars it is a spread, but I think that this is the kind of individual difference that what we were hoping or counting on was going to essentially balance between conditions, right? So for every person who has one conception of what a 4 is and somebody else thinks no, that should have been a 2 in the verbal condition, we'll similarly have people who have that diversity of things in the none or in the neural net both. And so the fact that the error bars got to be small enough on the estimates of the differences made us feel comfortable that those individual differences sort of came out in the wash. But definitely an experiment that we wanted to do, and then I should say as background. So this experiment, there were 4 of us involved in it. We were all at Carnegie Mellon when the experiment started, and only one person was still at Carnegie Mellon when the experiments ended. We all just for independent reasons, and so that really made it so we couldn't necessarily do the follow-ups we wanted directly. But I think that a follow-up we wanted to do was exactly to try and explore better, to get sort of better subjective measures. So, if somebody says 3, asking them questions like, okay, what would make it a 5? What do you wish you knew? And these kinds of things, trying to get at, which is tricky because it asks people to do a certain kind of metacognitive reflection, but really trying to get at a bit more clarity about, you know, what for individuals did they care about? Because then if we know that, you know, this is what Emiliano cares about, this is what David cares about, we might be able to explain better any differences in perception.
Thank you very much, David, for this answer. I don't know if there are other questions coming from the audience. And maybe we have time for one last question. And yeah, otherwise, maybe I have a curiosity, if I have time, if you have time. It's a kind of meta level question, maybe a forecast for you, from you. And I was wondering, after your talk, if the explanation we can generate are doomed to be local and domain dependent, or we can think of a kind of general explainable AI, with a system that can provide explanation regardless of the domains, and if you think that that is something that we can achieve in the future. So thank you.
Well, yeah, no, it's a great question. I think that's exactly part of the reason. I mean, I think there's many reasons, but one reason why people have leaned towards internal explanations. Because I can explain the way that an internal combustion an internal combustion engine works, whether it's in a car or a lawnmower or an airplane. I mean, I can explain how this engine sort of works internally. I can't explain whether the engine is sufficiently powered or whether it's the right tool for something without thinking about now domain-specific issues. So I think that much of the focus of explainable AI techniques to date has exactly been on trying to have things that are domain independent. Line doesn't care what the data actually represent. It doesn't care what the numbers correspond to. It's a method that just it operates on a mathematical function. And SHAP operates on a black box that is treated just as a mathematical function. You change the inputs and that changes the output. Okay, what is the mathematical dependence there? So I think the existing systems that we've been building are exactly the kind of domain independent thing that you're pointing to. But my view is, you know, that might give us at best a kind of explanation schema, but the actual explanation is always going to have to be grounded in the facts, right? Whether, you know, should I care that the outcome depends on variable X if I'm thinking about bias? Well, maybe if it's loan approvals and variable X is income, it's just fine that the outcome depends on that variable. If the variable is somebody's sex, then no, it shouldn't matter, right? So the content of the variables matters. What the numbers correspond to matters when we're trying to give actual explanations of the world or whether something is, especially if we want to give any sort of external explanation. So you know, I feel like they're useful tools, but they're always going to fall short of the explanations that we want and need. And so, of course, my colleagues in data science don't like it when I say things like that because they want methods that are truly domain independent. But I just think that when we're trying to understand all of those functional things, all of the reasons why we care about explanations, you know, all of these are all going to depend on the sort of facts on the ground. What's the domain? What are the constraints? What are the histories? And those are exactly the kinds of things that current explainable AI ignores. Do I think we could come up with a domain independent system for generating these kinds of, you know, local explanations? Sure, I think we could have domain independent practices to generate them, but it's always going to depend deeply on the facts on the ground.
Thank you very much, David. That's very interesting. As always, I mean, when you are on stage, and I don't know if there are other questions coming from the audience. Maybe we have one last question. That's the last one. So thank you, Anna Maria Silvana De Rosa. You can ask your question.
Do you hear me now?
Yeah.
Yes, now we do.
Oh, okay.
Thank you.
Sorry, probably the question is, related to the fact that I connected just a few minutes later. So I don't know if you have provided some information about who are the sample that you have interviewed. I mean, is there, for example, a differences between people in terms of expertise or experience, or to have a technical background, or to be completely naive? Also, I don't understand which is, AI for me become a little bit too generic. Are we speaking about chat GTP or in general or robot? You know, I would like understand a little bit better if there are hypotheses related, because this I start to think that you are opening a new field of research, which is the psychology of people interacting with the machine depending on their own representation, no? And I am really interested in social representation, the dynamic between expertise and lay knowledge. So, sorry, I don't know if I was clear.
Oh, very clear. And you're asking wonderful questions. I don't know that we're opening a new frontier. I think a lot of people have been starting to move in this way. I think we're just contributing to it. So our population for the experiments, we deliberately wanted populations that were not, we deliberately did a broad, we used an online platform, Prolific. We deliberately did not specialize it just to people who had technical expertise, because what we were really interested in is whether these are useful, the credit applications, are the explanations useful for a loan manager in a regional bank who has no technical understanding necessarily. So we were interested in the responses of people who didn't have technical training. Now we did ask how much technical training people had because we thought that might matter. And in our population, the vast majority of people did not have very much, and even the variation we saw it didn't matter. It was uncorrelated with responses and these kinds of things. So as long as people weren't hyper experts, the results seemed to be true of an enormous swath of people, and that's what we were really interested in. Now, I think where you went with that in terms of the importance of thinking about representations, prior expectations, do people know how to think about these systems is incredibly important, because one of the things that I didn't focus on this, but one of the things that we found here, but I've also found in other experiments that we've done on how people use the outputs of AI systems, work with Sina Fazalpour and Zach, trying to blank on Zach Lipton, is the importance of having a kind of match between how the system actually works and how people believe the system is going to work. That oftentimes the problems that result or failures to use the information correctly are not because people don't understand the output, but because they think the output is generated in a very different way than it is, or they think it should have been generated differently, right? So they think, I know how the world works. Your system is bad, so I'm going to reject the outputs that your system is giving me. So I do think that that's a factor that in our experiments, our community-wide experiments, I think we need to be much better about eliciting people's prior beliefs before they walk into the experiment. And so that's actually something I may have skipped over it with the bias experiment, the third experiment, but that was one that we actually did elicit, and we again find the match or mismatch between prior expectations and the performance of the system really matters. So there's all of that. I think you're right to ask about the reason I say that that's very important is because as AI broadens, as we go from decision trees and neural nets to things like large language models, where we can have different kinds of interaction, I think one important thing is that it now really matters what mental model people, especially those who are not trained in these systems, what mental models do they have of how the large language model works?
Mm-hmm.
And all of the early evidence is that people are completely wrong about how these systems work. Like people have completely misguided prior beliefs about how these systems function, why they're successful, and all of these kinds of things. So I worry a lot that um, to bring explainability techniques to large language models are they're going to fail in ways that lead people to expose themselves to harms they ought not.
Thank you so much. It was very, very interesting what you say. And if I just can add, may I just a short note? I am particularly interested in this period to understand because what you are saying is really related to social representation, because it is not just a pure cognition. Cognition also depends on the representation you have of this, let's say, other. No? So my question in this period is, for example, the chatbot an object, a subject, or an alter of the semiotic triangle? And depending on which is your representation, you find very different, let's say, conception of the AI, but not only among lay people. I am reading an immense literature, and I also see a very big and famous expert having still a lot of controversial representation of the AI. I am now using AI, but in particularly Gen AI.
Yeah, no, that's right, and I think the big issue there is that various powerful players in industry have an interest in getting people to think about the systems in a specific way. So sometimes it's that the experts actually, I think, misunderstand their own systems. Sometimes it's that they have an incentive to convince everybody that this is the right way to think about the systems. And maybe that's a very cynical way to think about it. But I do think some of the things that are coming from experts and from industry experts, especially, are trying to shape the narrative of how we should conceive of these systems so that people think of them in ways that increase trust, misguided increase reliance, increase utilization. Even when we those of us who don't have a vested interest in that, even when we think actually maybe we shouldn't be relying on them in the same way. So I think it's an incredibly challenging social and political problem as much as it is a technical one.
Perfect. Thank you so much. Thank you. Very interesting.
So thank you very much, David, one more time, and I guess we can stop here. And thanks, thank you again one more time for your availability and your expertise on these topics. And hope to see you again on the next Finance Online seminars.
Exactly. Thank you so much, everyone, for coming. It's been a real pleasure. Take care.
Bye.